Press fits, force fits, or shrink fits may be used for crevice-free permanent joints only when welding or soldering is not practical. So this is not a free and open application of using press fits. There has to be some demonstration that you can't do it any other way. The joints have to be usually to assemble metallic parts, having circular cross sections, free of shoulders or relieved areas. They're all, again, listed for specific applications, so it may only be for support pins or a stop pin on a seal face or a seal retainer. If they use them, the press fits for metal to plastic or plastic to plastic joints, there needs to be some supporting documentation available to demonstrate that those materials, which are much softer obviously than metal to metal, do in fact form a satisfactory seal. Particularly in metal to plastic, the differences in coefficients of expansion, you're operating at 40 degrees for the milk and then you hit it with 180 degree water during cleaning. What does this do to these two different materials? What does it do to the joint? What does it do to it over time? So the tightness of the press fit needs to be validated and make sure that there's no migration past the seal. EHEDG is a similar group located in Europe. It is the European Hygienic Equipment Design Group. They write guidelines, not specific product standards, in Europe. They've published a number of documents. Some of the more useful ones for us is they have developed a number of tests, procedures. This one here is a test for bacterial tightness. They are test methods that have been demonstrated to be effective, to demonstrate things that we need to know, so rather than reinvent the wheel, we get their input as well when we're developing documents, so that equipment coming from Europe going to the United States, or in the rare occasion when U.S. equipment goes to Europe, there is this harmonization of what's expected. Here are some examples of press fits. These are all acceptable press fits that you can have. The sealing points obviously are right at the top edge here, these top edges. So that's where the sealing points are. You see a shoulder here? Why do you think this one is an acceptable press fit? The reason is that the seal point is way up here. So in effect, that the shoulder is not of sanitary significance in this particular design. What we don't want is a surface press fit with this type of shoulder, where the shoulder is on the top. The reason being that there is no method available for machining these surfaces smooth enough that you can actually get a tight fit, and what all you've done is created a crevice here. That capillary action will pull in microbes, anything else. So when it says no shoulders, they mean no shoulders on the top part, because there's no way to seal this crevice here. This is not sanitary. You cannot clean it. The other thing it says is that no cracks or crevices. So you don't want whatever's put in here to be chamfered as a leading edge to push it down into the thing. And then having this little pocket here. Correspondingly, you don't want to chamfer on this side and have the other thing, because you're going to get a pocket or a crevice that's non-cleanable. There's a decreasing angle. Things will collect down here in the bottom and you'll never get them out. The mechanical force seal, again, which is a specialized seal, here again that are used on many valve types. The tightness of that seal, again, has to be validated so that they can demonstrate that there's no migration past the seal. The interior of the gasket groove shall be designed so the groove is inspectable and cleanable. Now that's not inspectable on a daily basis, obviously, since the definition for mechanical force seals said that these were not necessarily removed on a daily basis. But these seals might be on a rising stem compression valve that has like a triangular groove in them. And then the seal will be out like this. So the seal points once you put them into the groove, they have to be designed and toleranced so that the groove is completely filled and that the seal points are right on these outer edges. You want relatively sharp points. Fabricators will complain. Users will complain. Well, that cuts the gasket. It reduces the life of the gasket. Too bad, so sad. The object here is sanitation, public health considerations, eliminating of the cracks and crevices. Gaskets are a consumable. They don't last forever. So the mechanical force seal is a very specialized arrangement on commonly used on valves. The manufacturer shall provide a field replacement procedure for these seals that has been validated to reproduce the factory installed seal. Many times they'll ask for the stems to come back and be done at the factory. Even the fabricators don't like plant maintenance people messing around with them, because if the edges get dinged or banged up, then they don't seal properly. The surfaces behind this, which is looking at if the gasket is out, that there's a big enough opening here that you can see into where the gasket was. If the gasket fails, product gets behind it, that once you take the gasket out, that the area behind the seal is inspectable and cleanable. Rubber and rubber-like materials and plastic materials and the carbon and ceramic seal components may be bonded. The important is that the bond shall be continuous and mechanically sound. So if you're bonding, if you've got a stainless steel substrate here and you're bonding whatever it is, rubber, plastic, gasket, you want the bond to be complete here, so that there is no possibility that the material can separate from the base material, that you don't have little flaps, gaps along the edge. It's got to be continuously sealed to prevent things from migrating underneath. So the bond has to be mechanically sound and it has to be continuous. Typical of what you might expect on coatings, platings, things like that. They shall be free of delaminations, pitting, flaking, spalling, blistering, and distortions. Coatings also include, it's a special type of coating called an overlay, but these are the types of things that you see on PD pump impellers. The heavy rubber material of the impeller, which is overlaid over some type of metallic core. Some plug valves or rising stem compression valves have the round solid rubber bottom. These are, unlike a plating or something, which is, only 3 or 4 or 5 molecules thick. Overlays are quite a thick piece of rubber. But you want to make sure that they don't start to peel apart, they don't start to delaminate, you don't get blisters or cuts and things in them. The format and style manual also has some additional requirements when you get into different types of coatings and platings, how thick the coating has to be, if it's on a stainless steel substrate versus a non-stainless steel substrate. There's differences in the requirements of those coatings. From a practical standpoint, that's a criteria of use by the fabricator. There's no way for you folks to know how thick it is just by looking at it. Like I said, the standards are written for all three of the groups, and you have to get into what are important for the fabricators and users as well. As far as cleaning is concerned, there's two boilerplate paragraphs that will generally show up in all standards. Is this one that the equipment intended for COP or manual cleaning shall be designed and fabricated so all product contact surfaces are readily accessible. You can get at them all. And they are inspectable, either when they're installed position or when they're removed. So if you take, say, a personal access port, that all of the parts come off relatively easily, you can get at them from a safe working location and get them out so they can actually be cleaned. With the exception of pipelines, there probably is no piece of equipment that's truly 100% CIP. There's always something on it that you got to take off and clean. Even on a silo tank, you got to clean the door separate. You got to take the door gasket off. You might have a sample cock in the door that has to be hand cleaned. So even a piece of equipment that is generally recognized as CIP-able has appurtenances that you've got to treat manually. Equipment intended for CIP, cleaning shall be designed and fabricated so all product contact surfaces, including all non-removed appurtenances, can be CIP cleaned. Junctures between components shall be sealed or designed for manual or CIP cleaning. And what this basically is saying, in the crux of the whole thing of what is CIP-able versus non-CIP-able, is you got to get rid of the cracks and crevices and dead ends. That's the only thing that truly makes something CIP-able. Any surface that is potentially wetted by product has to also be wetted by cleaning solution with sufficient turbulence and flow to clean product out of it. Another important aspect of sanitary design and equipment is that surfaces shall be safe draining except for normal or typical clingage or adherence. And that may vary by product. Whey products drain very well. Condensed product, ice cream mix, more viscous products don't drain quite so well. So typical or normal cleanage. What you don't want, obviously, is pools or areas where product collects. If you can't make something self-draining, it is permitted to make something drainable for that you have sufficient drain points so the equipment can be drained. Again, I'll use the pump. This is a very good example. Everybody's familiar with a centrifugal pump. Is this self-draining? No. It'll only drain to here. The bottom half of the pump housing is full of water. Unless you turn this outlet down, which is very common pump installation in Europe, not so common here in the United States, but a pump is not considered as self-draining. And some valve housings are not self-draining. You'll have a little ring of solution or product remaining in certain valve housings, depending on where they're located. But here again, if you take the plug out, they'll drain. Obviously, in the fluid milk industry, you have very strict requirements about added water and adulteration to products, how much water can be added, like from a steam injector or steam pasteurizer. You have to balance it out back to the original components. On the manufacturing side of the industry, additional water in the system, as long as it's just clean, flush, potable water, makes no difference. So the amount of water is in some respects dependent upon the process and the product. What the sanitary design is that, first of all, the system needs to be designed that there's no residues of cleaning solutions left in the water. that it's strictly a potable water rinse. It'll be flushed to drain before they start on product. So there are operational and inspectional considerations, but they're not part of 3A.